This is our lecture number 19, and in this lecture we're going to continue discussion of the chi-square test and chi-square distribution. So how else can we use the chi-square test? So in the previous lecture we discussed how we can use the chi-squared test for something that's called goodness of fit. So this test involves collecting one sample of data from a single population and comparing the percentages of different responses. So the data that we collect, it has to be categorical, not numerical data, and we're comparing how the data, how responses, different categories in the data are distributed regarding the certain distribution of proportions, probably, right? That's the best way to put it, I guess. So in other words, we believe that certain distribution of proportions exists among the responses, and we're just testing to see if the distribution in the data of the same proportions for the same categories actually matches something that we believe in, some predefined percentages how the responses should be distributed. So chi-squared goodness of fit test was actually test about multiple different possible categories from a single sample, from a single population. So what we're going to discuss today is test for independence, and this is where we're actually starting to get into the concept of how one variable can depend on another variable. We're going to discuss that topic in much more details a little bit later, about a couple of lectures down the road. We're going to start regression analysis. So without further ado, let's get started. So we used chi-square again to test nominal data with more than two categories, multinomial, and we just wanted to see how nicely the data fits certain predefined proportions, percentages. Okay, so what's the test for independence? Let's say we have two variables, x and y, and in this case, for the chi-squared test, we're going to assume that both x and y are categorical. For example, nominal. It can be ordinal as well, in which case the order is not really important. So ordinal data we're going to just consider as nominal or categorical data, without paying any specific attention to the orders of different categories. But more frequently this test is applied to purely nominal data, when we just have categories with no order in between them. Here is the example that we're going to actually discuss in this lecture. It has nothing to do with business, probably, although who knows. So we'll see. Does a pet preference, cat or dog? So as you know, people pretty much are judged, are you a cat person or are you a dog person, right? Some people like cats more, some people like dogs more. So does a pet preference depend on the gender? So in other words, do men and women share the same pet preferences, or specifically, if we're going to ask, for example, men, which ones do you prefer, dogs or cats? So we're going to collect the data, and we say, for example, find out that 60% of men prefer dogs and 40% prefer cats. Will these percentages hold the same when we are going to ask women? So in other words, if we're going to ask women, bunch of women, what do you prefer more, dogs or cats? And we're going to collect the data, and then we'll calculate percentage breakdown. If women demonstrate the same percentage breakdown, for example 60 versus 40, then we're going to say it doesn't matter who you're asking, right? All people, regardless of their gender, male or female, they like dogs and cats in exactly the same way, right? Certain percentage like dogs, certain percentage like cats, and it doesn't matter if you're male or female. In this case, we're going to say that pet preference and the gender, male, female, are independent variables. If, on the other hand, we're going to find out, let's say, just again, for example, that among females, 50-50, 50% like dogs, 50% like cats, but in the males it's 70-30, 70% like dogs and 30% like cats, then we're going to say, whoa, well, that really depends on who you're asking, right? What do you prefer, cats or dogs? In this case, we're going to say that the pet preferences and the gender are dependent variables. Okay, it depends on who you're asking about the pet preference. If you ask females, you'll get one type of response pattern. If you ask males, you get another type of response pattern. Okay, so this is a data-driven course, so we're going to look at the example. We collected the data. We asked 100 people randomly, and some of them were men, some of them were women, right? So it was a completely random sample. Who do you prefer, cats or dogs? So each person, we recorded 2 things about each person: their gender, male, female, and what they like, dogs or cats. Okay. So here's the question that we're going to have to answer by the end of this lecture. Can we conclude at 5% significance level? So we're going to have to test hypothesis, obviously, right? That pet preferences depend on person's gender. So therefore, pet preference and the gender are dependent variable, or it doesn't matter, in which case they're independent variable. Okay, so let's go back to our big fat analysis flowchart, right? So here's what we're doing really. We're testing for a relationship. Does the relationship exist between gender and the pet preference? Okay, so we're starting right here. That basically is untapped territory for us, right? So we never looked at the relationship between the 2 variables. Okay, so, and in fact, you know what? Let me go ahead and get the data in. So I'm going to call my data frame pets underscore data, and that is coming from the file read CSV, C data folder. Pet preferences, if I remember correctly, pet underscore preferences dot CSV. Oh yeah, okay. Alrighty, so let's take a look at the structure of the data. Pets data. And here it is. Okay, I have 2 columns. Gender, male, well, probably down the road I have female somewhere, right? And pet, what pet do they prefer? So, and you know what, let me go ahead and show you basically what the data looks like. Alright, in Excel pet preferences, there you go. So here's my data. Okay, so I asked 100 people, right? So there you go, I have 100 people. The first person that I asked was male, and they preferred the dog. Second male also preferred the dog. If I scroll down the road somewhere down there, at some point male started to say cat, right? So obviously they're ordered, right? So these are not just randomized answers, which doesn't really matter for our purposes, but yeah. So at some point male started to say I like cat, right? Then after that I started, like, in my sample, it's completely random sample, right? I got females, and the first group of females I recorded preferred dogs, right? And then after that were females preferring the cat. Okay, and that's it. So that's how my data are organized. Okay. So let's discuss a very important, well, I wouldn't say it's a graphical tool, but it's certainly a summary tool for data that is used a lot in statistics and data analysis in general. So if later on, when you're in the School of Business, you're going to take a course, Introduction to Data Analytics, we're going to use that tool actually a lot in this course. Okay, and that tool is called Contingency Table. Okay, so I'm going to write it out. Contingency Table. It's kind of a long name, right? So the abbreviated name for the same tool is cross table, or so it's also known as, right, aka cross table, or simply cross tab. Okay, cross tab. So this tool basically gives us a summary in form of the table how to nominal variables, and in this case I do have nominal variables, right? Variable gender has two values, and you can see it's a character, right? So it basically categorical nominal male female, and variable pet also has two values, dog and cat, right? So cross tab, which I'm about to create, actually is an attempt to summarize simultaneously the distribution of two categorical variables. In my case, it's nominal variables. Okay, so I'm going to use the same exact function that we did before. Okay, so for example, here's what I can do, right? So I'm going to say males counts. Okay, so this is how we used function table before. Male counts. Okay. No, gender count. Sorry, not male. Gender count. Okay, so I want to know in my file how many males and how many females I have. I know that in total it should be 100 people, right? So I'm gonna say table, summarize the column, what, gender, right? So I'm gonna have pets data, column gender, summarize gender for me. Okay, gender counts, and let's take a look at how the genders are distributed. So we asked 100 people, and out of them, as you can see here at the bottom of the screen, right, 48 were females and 52 were males. So it's close to 50-50, not quite like that, right? So it's random. Okay, so now I'm going to say pet preferences counts, right? And again, I'm going to use the function table. All right, and pets data. It's not quite where I wanted it to be. Pets data, $, column called pets. And let's take a look at how the pets are distributed between these 100 people, right? 43 said that they prefer dogs, and the rest of them, 57, said that they prefer 43 prefer cats, and 57 prefer dogs. Okay, so that's how responses distributed separately as far as gender is concerned, and as far as the cats and dogs are concerned. Okay, and I can also calculate. I know it's 100 records, right? But let's be formal about that. So n row in my data set, pets data. Okay, and then I write out the n is 100. Okay, now I'm going to create a contingency table, or cross table, or cross tab. That's a more complicated representation, slightly more complicated representation of the same very data set, and now it takes actually in consideration both columns with pets and columns with gender. So here's how I'm going to do it. So I'm going to call this variable cross underscore table. Okay, and I'm going to use the same exact function table, just what I did before, to get the summaries of my column 1 and column 2. But now I'm going to ask R to create a tabular summary of two variables simultaneously. So for example, variable number 1 is going to be pets data gender, comma, variable number 2 is going to be pets data $pet. Okay, alright, so I just created a cross table, and now I have to show that. Bam. Alright, essentially it gives me same information and a little bit extra. Okay, so first of all, how is it the same? Well, I know that in my in my data file, right, 48 people were females and 52 were males. And look at that. Here is the female who like cats. There were 19 of them. And here are females who like dogs. There were 29 of them. And if I add these two numbers together, 19 plus 29, I'm going to get 48. Okay. So, but this time around, look at that. It doesn't just give me the count, count of females. It says, well, here's how females are broken down between cats and dog lovers. Okay. Same thing about males. So, males who like cats, 24 of them in my sample, and men who like dogs, 28 of them. If I add these two numbers together, I'm going to get 52, right? And that's precisely what I was getting before. but now I'm getting more details, right? How males are distributed between the cat people and dog people, right? And same about cats and dogs. So cat, for example, right? Out of all people who like cats, 19 were females and 24 were males, for the total of, if you add these numbers together, 19 plus 24 will give you, what, 34 plus 9, that's 43, right? 34 plus 9, 43. And there you go, that's your 43. And dogs, 29 people who like dogs were females, and 28 in my sample were males. If you add them together, you're going to get 57, right? And there you go. Okay, so essentially this table is more contains more details, right? I can still get the same information, what's the breakdown for, between males and females and cats and dog people, right? But also it tells me how exactly females are structured in terms of preferences, cats and dogs, and same thing about males, right? So this is called cross tab. Okay, this is the tabular summary again that represents simultaneously the distribution of two categorical variables. In that case, two nominal variables, right? Cats, dogs, that's pet preference versus gender, male, female. Okay. All right. Now let's go back to the test itself. Okay. So this is cross tab, and let me go back to the analysis flow chart, right? So here's how we can use analysis flowchart in order to find out that in this case we're going to use the certain specific test. So I'm talking about the relationship, right? Is the are the pet preferences related to the gender? Is there a relationship between them, or are they completely independent? So this is where I'm starting. Data type. Well, I know it's nominal, right? And there you go. It tells me immediately that if you have if you want to find out if variable x, gender, is related or not related to variable x, dog preference, pet preference, right? And you're dealing with nominal data, then you're going to have to do the chi-squared test of contingency table. And that's what I wanted to emphasize. This is the contingency table, okay? This right here is the contingency table. So it's a tabular representation of distribution, simultaneous distribution of two categorical variables. In that case, nominal variables. All right. Let's go back to the lecture notes. There you go. So here is the idea, and on these slides, I basically summarize the same exact info that I just discussed with you, right? So if you add together females, right, 19 like cats and 29 like dogs, you're going to get total females. Same for the males, and same thing for the cats, right? If you look in columns, then if I add together male, female that prefer cats, that's total cat preferences, right? Okay, so how do we perform the test? First of all, here's how we formulate the hypothesis. So our null hypothesis will always state that variable x in your data set and variable y in your data set are independent from each other. And the alternative will say opposite. If they are not independent, they are dependent, right? So what does that what does that really mean? Here is basically how we interpret that. Oh, here we go again. Another call. Hold on just a second. Alright, sorry about that. It happened before, right? Okay. You're kidding me, right? Okay. Somebody picked it up. Alright, so here is basically what that means, right? So let's go back to the previous one. Here's basically what that means, that the variables are independent from one another. If the variables are truly independent, and my null is true, that means that the percentage breakdown of females who like dogs versus females who like cats are exactly the same as the percentage breakdown for males who like dogs and for the females who like cats. So in other words, if I will find out that among females 60% like dogs and 40% like cats, and among male also 40% like dogs and 60% like dogs and 40% like cats. And I'm going to say, doesn't matter who you are, male or female, you're going to like dogs versus cats just the same. So in this case, pets, preferences, and gender are not dependent on one another. Okay, but if I find out that, and by the way, in this case also what I can say is, in society in general, male, female together, the breakdown for the cats and dogs is 40-60. Okay, 40% like cats, 60% like dogs, for example. If on the other hand I will find out that the percentages are different for males compared to females, for example 50-50 for females and 70-30 for males, okay, now I'm going to say it depends on who you are, male or female, what do you prefer, cats or dogs? So the percentages are not the same. Okay, so and here's how the test is conducted. Just like before, if you remember our previous lecture number 18, when we discussed goodness of fit, the idea was basically is to calculate the actual frequencies, okay, of responses. So in our case, the responses, there are 4 of them, right? 2 for cats, dogs, 2 for pet preference, and 2 for female, male, gender. Okay, so overall there are 4 responses, right? These are actual frequencies that we have observed in our data set, right? Frequency 1, frequency 2, frequency number 3, and frequency number 4. Okay, so and then I'm going to assume, if you remember how we start hypothesis testing, always we assume that the null hypothesis is true. So what is null hypothesis? Null hypothesis is that percentages breakdown of cats versus dogs preferences are the same for males and females. In other words, gender and pet are independent from each other. Variables are independent from each other. And I'm going to assume that the null is true, that the percentage of breakdowns is exactly the same for males and females. I'm going to calculate the expected frequencies. What I expect to happen in the male portion of the sample and in the female portion of the sample. I mean, what are going to be the counts, right, of dog lovers versus cat lovers for males and females, if the null is true and the preference is exactly the same for males and females. And after that, I'm going to use I'm going to use the same exact formula right there, okay, for the chi-squared that we used before to test the goodness of fit. So I'm going to take the expected, the actual frequencies, subtract the expected frequencies, square divided by expected, add together among all categories, right? All possible combinations of responses, okay? And the idea is this: if my frequencies that I observe and the frequencies that I expect, if the null is true, are exactly the same, then differences are going to be zeros, and the entire chi-squared sum is going to be 0. So in other words, if the null is true and expected frequencies and the actual frequencies are the same, that means that I have chi-squared equal to 0, and I have evidence that my null is perfectly true, right? What I expect the frequencies to be, if the null is true, that's exactly what they are. So if chi-squared is 0, then I have overwhelming support for my null hypothesis. But as soon as my actual frequencies start to be different from the expected frequencies, if the null is true, and chi-squared is starting to get a value, right? And the bigger the differences, the bigger the chi-squared value. So just like before in the previous lecture for the test of goodness of fit test, right? The higher chi-squared value, the more evidence I have to support my alternative hypothesis, okay? And again, what I'm looking for, where my p-value is, it's in the right tail of the chi-squared distribution, okay? So that's the idea. Alright, so let's go ahead and proceed. So here is how I propose us to proceed, okay? Let's do the calculations. So I know that these are actual frequencies, okay? So females who like cats, I'm going to write it down. My F1 frequency is 19, right? So in this case, I'm going to be actually very explicit. The second frequency, females who like dogs, is 29. Okay, that's the actual. 24. F3 frequency number 3. That's male. Males that like cats, 24, and my actual frequency F4 is all males who like dogs, 28, right? And if I add them together, I should get 100. So now I'm going to run that. So now let's see what are the expected frequency if the null is true. First of all, let's calculate the percentage of cats and dogs. Okay, so I know that these are my counts right there, right? So I have pet preference counts right here. Okay, I can calculate pet proportions, right? Percentages. So pet preferences proportions. It's kind of a long name for the variable, but who cares, right? Prop dot table, and I have to feed the prop table that variable that contains the counts for me, right? So let's do that, and let's see. Well, I kind of know what to expect, right? Out of 100 people, 43 preferred cats, that's 43%, and 57 preferred dogs, that's 57%. So that's exactly, no, hold on. That's exactly what I see right here. 0.43 is the fraction of all of my sample, right? Male, female, everybody together that prefer dogs, and 57 is the fraction of people who prefer 43% prefer cats and 57 prefer dogs. Okay, wonderful. So now I assume that my null is true, right? Always, in any situation, all tests are done exactly the same way. We start by believing that the null is true. Okay, if the null is true, that means that the same exact percentages should apply for two females as a group, right? And to the males as a group. Okay, so expected count number 1. That would be females who like cats. Okay. Alright, so what do? I am going to take the count of females, which is 48, right? There are 48 females in the sample. So out of 48 females, if null is true, out of 48 females, 43% would prefer cats. So if I multiply that by 0.43, and I'm going to find that E1 frequency is going to be 20.64. Okay, if null was perfectly true, then 20.64 out of 100 females prefer cats. Now note that the number is not integer, right? I mean, most of the time you're going to end up with a fractional number. Now the question is, okay, how is that possible, right? It's not possible. It's either 20 or 21. Okay, for now we're going to stick with this, right? For now we're going to say, yeah, it's all averages, okay? So we're not going to round anything up or down. We're going to stick with what we got, okay? So this is my expected frequency. The actual was 19, right? If null was true. Oh, no, the actual is 19, but if null was true, then that number should have been 20.64, okay? How about E2, expected frequency number 2? That's what I expect to see among females if null is true, and these proportions apply to females, right? And in this case, out of 48 females in my sample, 57% would prefer dogs, right? So I multiplied by 0.57. Now let's see the number E2. So if null was perfectly fine, and 57% of males and females would prefer dogs, then out of 48 females, 57% would prefer dogs, and that would correspond to the count 27.36. Again, don't worry about the fraction. This is just a test. Okay. Now let's switch our attention to the frequency, expected frequency 3, right? E3. E3 corresponds to males that like cats, right? The actual frequency F3, males who like cats, was 24. What would be the expected one? If the pet preferences, cats versus dogs, and the gender male-female are truly independent, then this same exact breakdown for cat lovers and dog lovers would exist among males and females alike, right? So that means that out of 52 males in the sample, I would expect 43% again to prefer cats, right? So my expected frequency would be 52 males altogether, 43% of them like cats, and I run this one. So E3 says if null was perfectly true, then out of 52 males, 22.36 would prefer cats, while in actuality my count was 24, right? So this is the expected frequency if null was true. This is the actual frequency. And the last one, expected frequency number 4, that would be what do we expect to see in the male portion of the sample if null was true with respect to do they like dogs, right? So again, among 52 males, right, what percentage would like dogs? 57, right? If null was true, and this breakdown 43 versus 57 would apply to both males and females alike, and 57% of the males would prefer dogs, and I multiply 52 count of males by 57% of them like dogs, and my expected count number 4 would be 29.64. That's the expected, while the actual was 28. Well, you know what? I'm looking at these numbers and they're not that far away from each other, right? Expected frequencies and the actual frequencies are not that far away. If null was true, I would expect 20.64 females to like cats, and that was 19, right? So if you consider F1, F2, F3 versus E1, E2, E3, F4, right? They're not that far away, okay? That's just informal assessment, of course, right? Test will tell us exactly are these frequencies consistent with the fact that it doesn't matter who you are, male or female, you like dogs and cats the same, or are they too far away? But just by looking at these numbers, I'd say, yeah, they're not that far away from each other. So probably null is true. That's just my informal assessment again, okay? So now let's go ahead and continue, right? So now I'm going to calculate my chi-square value, okay? And how do I calculate that? Well, remember the formula. Formula looks like this, right? Frequency minus expected squared divided by expected. All right, so let's go ahead and do that. Because the R studio or R can be used as just big fat calculator, I'm going to create a big fat expression, and I'll see what happens, right? So frequency number 1 minus expected frequency number 1 squared divided by expected number 1 plus frequency number 2 actual minus expected number 2. Right here I need to correct, okay. That would be squared divided by expected number 2 plus third category, right? Frequency number 3 minus expected number 3, that all squared divided by expected number 3 plus frequency 4 minus expected 4 squared divided by expected 4. And that's it. That's what Christmas is all about. Okay, so everything appears to be in order, so I'm going to run that. You know what I did? Do you see the red stuff? It says, my friend, you're doing something wrong. Here's what I'm doing wrong. Here, instead of underscore, I insert a dash, which is minus, right? In the world of software, dash is minus, really. So I have to insert underscore. Okay, so. Alright, now I calculated the chi-squared value, and let's go ahead and find out what the chi-squared value is. It's 0.4396, and I believe I have the same exact calculations. Let me just double check. 0.439643. Yeah, I have the same calculations in my slides. Okay. Now that is my chi-squared value, and now the p-value is, again, just like before, it's the tail, it's the area in the right tail of the chi-squared distribution, right? Because what do we mean by values more extreme than that? Okay, closer to 0 chi-squared support the null hypothesis, right? away from 0 chi-squared values support alternative. Okay, so this is the one that I calculated. This sample gives me chi-squared of 0.4396, right? What's even more extreme than that? Even larger values. So that's why each time when we test chi-squared, when we perform the chi-squared test, the p-value is in the right tail of the distribution. Now, the only one thing that's remaining is how many degrees of freedom, right? In the previous lecture, when we tested the goodness of fit, right? Number of degrees of freedom was k minus 1, where k is the number of categories. Now, in this case, I don't have number of categories, right? I have actually variable x, gender, male, female, and I have variable y, which is pet preference, cats and dogs, right? Both of them have 2 categories, right? So what do I mean by number of categories? Well, here is how number of categories, or degrees of freedom is calculated, okay? It's number of rows, categories for variable number 1, number of rows, minus the number of categories, times number of categories minus 1 for another variable, right? So rows minus 1, columns minus 1. Rows is how many categories you have in gender. Columns is how many categories you have in pet preferences, right? So for rows we have 2, right? Male, female, minus 1 is 1. For columns we have also 2, cat, dog. 2 minus 1 is 1, so 1 times 1 is 1. So I have to use chi-squared distribution with number of degrees of freedom equal to 1. Okay, so now I pretty much have everything that I need, right? So now p-value, I'm gonna say p-value is the area to in the right tail, or to the right from the p-value, the chi-squared value that I calculated, this one, 0.439643, right? 0.439643. Okay, so just like before, let's go ahead and use the function called how do we calculate the probability or the area? We're using the function p, right? P, in that case, is going to be p for chi-squared. Remember, pretty much every distribution has 2 functions, right? So at the beginning of the semester we use the function p norm, probability for the normal distribution, and q norm, that is value if you know the probability, reverse one, right? Then we use the function pt and qt, right? Same thing applies for the chi-squared, p chi-squared and q chi-squared. Okay, anyhow, so what are we looking for? We're looking to the right from this chi-squared value that we computed, right? So I'm gonna say chi-squared value. Next one is how many degrees of freedom you have. So degrees of freedom is 1, rows minus 1 times columns minus 1, and the tail of the distribution, lower, again, it's all done through the parameter lower tail. Well, lower tail is left tail, I'm looking in the right tail, so lower tail is false, and that should give me the p-value. There you go, p-value is 0.0573. Alright, so now let's go back to the hypothesis testing. So we have calculated and in the slides I have exactly all these calculations repeated, okay? And here is the graphically what's going on, okay? So I calculated my chi-squared to be that, and the degrees of freedom is 1, so now I'm using that function, probability for the chi-squared, lower tail is false. So this is what the picture looks like. This is my chi-squared distribution with 1 degree of freedom. I calculated chi-squared value from my sample 0.439643, and the p-value is the area to the right from that 0.439643, 0.5086. Is that what I was getting? 0.5072. Okay, so my slides are not quite right. 0.5072. Okay. All right. So now we have to conclude the hypothesis test. Okay. We know the probability to see sample like that, or with even bigger chi-squared value, is 0.5. 50% chance if the null is true, right? So question is that a high probability? Yes, indeed it's high, right? It's higher than anything that we can pretty much use, right? So since the p-value is higher than even the largest significance level 10% that we can use, so p-value is high, we fail to reject the null hypothesis. And what does the null state? The null states that variables gender and pet are independent from each other. In plain English, it means that if I ask a bunch of men, what do you like, what do you like, cats or dogs? And I ask a bunch of females, what do you like, cats or dogs? The percentage breakdowns in both groups are going to be the same. So the pet preferences do not depend on the gender. They're universal in the entire society across the gender. Okay, that's basically what the result is. Okay, so and that pretty much concludes this lecture, with one exception. Let me show you. So this was a long way, right? This was kind of a we had to create a cross tab. We had to calculate the expected frequencies, right? If null is true. And then we had to calculate the chi-squared value, and then use the p chi-squared function to see the area in the right tail. Can it be done shorter? Sure, of course it could have been done shorter. Let me show you. Okay, so I'm gonna put a comment here: shorter way of testing variables independence. Okay, so it's done by using the function chi-squared test, as you probably have guessed. Okay, so the only difference is that I have to feed the function the cross tab. Okay, so over here, if you remember, this line 17 in my code, okay, I created a cross table, right? So I tabulated two variables simultaneously together, gender and pets. Let me run this result to show you. So this is what we mean by the cross tab. Okay, so essentially it's a two-dimensional table that contains simultaneous distribution of two categorical variables, pets and gender in my case, right? So, and that's exactly what I have to feed into the chi-squared test. Okay, so I'm gonna have to say chi-squared test, take my cross table, all right, and look at that. If I run the test like that without specifying anything, it actually gives me a different p-value, right? My p-value was God, what was that? It's somewhere here, right? P-value right here, 0.5073, right? And now my p-value is 0.6449. Okay, so here's what the function chi-squared test does. Okay, unless I specify anything else, what it does is corrections. Remember when we discussed the expected frequencies, each one of our expected frequency was a fractional, right? So let me show you E1, for example. E1 was a fraction, right? So it's not 20 females that like cats, but not 21, but 20.64. Well, in actuality, we know it must be integer, right? So what chi-squared does is it says, really, you can't have fractions. Okay, so let's make corrections to make sure that your responses are not fractional but integers. Okay, so if I don't want the chi-squared test function to make these corrections, and I want to use exactly the expected values which I computed that contain decimal points, right? And I have to turn the corrections off, right? So in my function chi-squared test, I have to say correct equals false. Okay, so I'm going to say use the expected frequencies the way you calculate them without rounding them to the integers. Okay, so if you get 20.64, yes, that cannot be the count, but use that anyway, just like what we did when we calculated the chi-squared value, right? So, and when I run this line right there, there you go. Okay, so it gives me the p-value, which is pretty much what I was getting before, right? gives me 0.5073, and before that I was getting 0.5073. Same thing. Okay, so if you want to skip all these calculations, right, expected frequency chi-squared, and find the error in the right tail, you can just write this one single line, and you'll get the same exact result. Alright, that concludes our lecture on the how to test if two nominal variables are dependent on each other or they completely independent from each other. Okay, and in the next lecture we're going to take a look at another pretty fascinating test, which is called ANOVA, and well, you will see exactly why it's fascinating.